Okay, we're going to go through the Unit 2 review packet, working through each of the problems to show the solution. So the first question, it's a literal equation. We are solving for a. We multiply both sides of the equation by a to get it out of the denominator. And we get GA equals 1 plus 2a. Now we want to get all our a terms on one side of the equation. So I'm going to subtract 2a from both sides. So I will get GA minus 2a equals 1. Here I can factor out a, leaving with a, g minus 2 equals 1. And now if I have a times g minus 2 and it's equal to 1, I can divide both sides by g minus 2. And we get a is equal to 1 over g minus 2. This next problem appears to be similar. We have solve for x, and we are looking at x minus c over x. So we have a x in the numerator and denominator. So here I'm going to multiply both sides by x. I get g times x, or x times g, equals x minus c. If I want all my x terms together, I'm going to subtract x from both sides. I'm left with gx minus x is equal to negative c. Now here I can factor out an x, and I want to remember that just having minus x is the same as minus 1x. So when I factor out my x, I'm left with x times g minus 1 equals negative c. And here I will divide by g minus 1. We'll get x is equal to negative c over g minus 1. Next problem, solve for a. So we have u plus ka equals 3 minus ba. So I want to get all my a's to one side and all my other terms to the other side, and then factor out my a's just like before. So here I will subtract ka from both sides. And I can also subtract 3 from both sides. So on my left-hand side, I get u minus 3 equals negative ba minus ka. Factoring out my a, I end up with a, negative b minus k is equal to u minus 3. Now I can divide by negative b minus k. And we get a is equal to u minus 3 over negative b minus k. Yeah, I think that's pretty good. If we chose to do this slightly differently, say I had added BA to both sides in the beginning. So say we had ended up with, in our second step, KA plus BA. And then say I had subtracted U equals 3 minus U. Then I factor out my A, and I get A, K plus B equals 3 minus U. And then A equals 3 minus u over k plus b. So this is also a correct answer. These are two equivalent expressions. And we just have 3 minus u over k plus b versus u minus 3 over negative b minus k. So we can switch the negatives and positives and still have equivalent expressions here. And depending on your solving path, you might get one or the other, but they are the same. Okay, if we look at problem number 4, we're solving for x. I see all my x's are in this term, and so I'm going to isolate this term first, subtract by 2 on each side of the equation. So I get 2x minus 3y over 1 plus 3x equals 3a minus 2. Okay, I want to get all my x's into the numerator, so I have to multiply both sides of the equation by 1 plus 3x. And I have to multiply this side by 1 plus 3x as well. On the left-hand side of the equation, this cancels because I'm multiplying and dividing by the same thing. So I get 2x minus 3y equals, on the right-hand side of my equation, I have to make sure I'm distributing properly. So here, 1 distributes to 3a, 1 distributes to minus 2. 3x distributes to 3a, 3x distributes to minus 2. So I get 3a minus 2 plus 9ax minus 6x. so I have to make sure to distribute all the terms. From this point, I can look to combine all my like terms. I want all my x's on the same side. So here I will add 6x to both sides. I can add 3y to both sides. And I can subtract 9ax from both sides. So on my left-hand side of the equation, 2x and 6x combines to 8x, and then minus 9ax. On the right-hand side of my equation, I have 3a minus 2 plus 3y. Here we can go ahead and factor out the x. So we get x, 8 minus 9a equals 3a minus 2 plus 3y. Then we divide away 8 minus 9a from both sides. And that is our solution for x. X is equal to 3a minus 2 plus 3y over 8 minus 9a. For the next problem, we want to solve for x again. So first I'm going to notice that I have constant terms of 5 and 4. So I will subtract 5 from both sides, resulting in ab minus 1 equals negative q squared x plus 1 over 3x. I'm going to multiply both sides of my equations by 3x. And I'm left with 3xab minus 3x equals negative q squared x plus 1. I want to get all my terms with x on the same side, so I add qx squared to both sides, leaving me with q squared x plus 3xab minus 3x is equal to 1. Factor out my x. We get x q squared plus 3ab minus 3 is equal to 1, and divide by q squared plus 3ab minus 3. So these cancel, leaving us with this expression is equal to x. In this next problem, we have p squared x plus 3y over x minus 2 plus 6 is 11. So first things first, I'm going to combine these constant terms. Oops, we're going to subtract 6 from both sides. And we will get p squared x plus 3y over x minus 2 equals 5. Now I want to multiply both sides by x minus 2 to get x out of the denominator. And we get p squared x plus 3y equals 5x minus 10. Here I want all my x terms on the same side, so I'm going to subtract 5x from both sides. And I will subtract 3y from both sides. And we will get p squared x minus 5x equals negative 10 minus 3y. I can factor out my x. We get x times p squared minus 5 is equal to negative 10 minus 3y. And now we divide by p squared minus 5 on both sides of the equation. And we have solved for x. For this next problem, I want to solve for y. I notice that I have this constant of 4 and constant of 6/4 that I would like to combine. So I'm going to turn 4 into 16/4 so that it has a common denominator. And then I will subtract 16/4 from both sides. And I will get 2y minus 5 over y is equal to x squared. 6/4 minus 16/4 is negative 10/4. Okay, and I can actually reduce that down to negative 5 over 2. Here, I cannot cancel the y's. I need to multiply both sides by y. And I get 2y minus 5 is equal to, the y distributes to both terms, yx squared minus 5/2 y. And actually, I'm going to write this as x squared y. Okay, now I want all my y terms on the same side, so I will subtract 2y from both sides. And I get negative 5 is equal to x squared y minus 5 halves y minus 2y. So here I could factor out y, and I could divide by what my result is and solve for y. However, I would end up with a fraction within a fraction. So what I'm going to just do really quickly is I'm going to multiply both sides of my equation by 2 to clear out this fraction. So I'm going to distribute this to each term. So I get negative 10 is equal to 2x squared y minus 5 halves times 2. 5 over 2 times 2 gives us just 5y. And then minus 4y. And then I notice if I have minus 5y and minus 4y, these can combine to be negative 9y, or minus 9y. Now I can go ahead and I will factor out my y's. So I get negative 10 is equal to 2x squared minus 9 times y. I'll divide both sides by 2x squared minus 9. And I get y is equal to negative 10 over 2x squared minus 9. Okay, last literal equation, so I'm solving for p. I see I have p in this term, and this term. P is always in the numerator here. So I'm going to go ahead and get all my terms with p on the same side. So I will add pr squared to both sides. And we get pr squared plus yp plus zp over 3y equals 4 over 3m. So I'm going to show you what happens if we don't clear our denominators. So say we just go ahead and factor out p, which is completely fine. We get p r squared plus y plus z over 3y equals 4 over 3m. If p times something is 4 over 3m, when we divide by that exact thing, we should have an isolated expression for p. Okay. But what you'll notice is that this expression has fraction within a fraction and then another fraction in the denominator. And we kind of want to simplify this down into a single fraction. So what I'm actually going to do is I'm going to take this and I'm going to show us how we can do that. Okay, so if I want to look like how can I deal with this fraction within a fraction, I see my numerator is some fraction 4 over 3m, and then we have divided by my denominator r squared plus y plus z over 3y. So I'm going to use the fact that if I have some fraction a over b divided by another fraction c over d, I can use the fact that we can go a over b times the reciprocal d over c. And so in our example, a over b, or our numerator, is the fraction 4 over 3m, and it is being divided by, and now in our denominator, I want to turn this into a single fraction, because I see this z over 3y term, and these are like they are over 1. So I want to take r squared over 1 plus y over 1 plus z over 3y, and turn that all into a single fraction. To do that, I need a common denominator. So I'm going to multiply this term by 3y over 3y, and this term by 3y over 3y. So that'll give me 3y r squared over 3y plus 3y squared over 3y plus z over 3y. So now I have a common denominator, and I can rewrite this whole expression as 3y r squared plus 3y squared plus z all over 3y. And if I have one fraction now divided by another fraction, I can turn this into multiplication by the reciprocal. So I can say 4 over 3m times 3y over 3y. I'm going to turn my times into a dot. 3yr squared plus 3y squared plus z. And now I just have to use the fact that fractions multiply numerators multiply denominators. In the numerator, I will have 12y all over, let's see, 9ymr squared, distribute to this term, distribute to the next term, plus 9my squared into the third term, plus 3mz. So this takes our original 4 divided by 3m all over r squared plus y plus z over 3y, which has parentheses that are implied and that has fractions within fractions, and it turns it into a single fractional expression. So if we go back, and let's copy this. If we go back to solving for p, when we had this whole expression here, yes, that's solved for p, but we much prefer this type of expression right here, where we've combined it all under a single fraction. And then one last thing to note here with our expression for p is that we have 12, 9, 9, and 3. So all of our terms have a common factor of 3, so I can actually simplify this down by dividing each of the coefficients here by 3. So I can turn this into 4y plus 3ymr squared plus 3my squared plus 1mz. So that took our original expression here with the 12, 9, 9, and 3. We said they have a common factor of 3, and so we reduced down to get our expression for p. Okay, now we can look at our composition of functions. For our first composition of functions problem, we are given functions f of x, g of x, h of x, I of x, and j of x. F of x and g of x are linear functions, h of x is an absolute value, I of x is a quadratic, and j of x is an exponential function. And so we're just evaluating composition of functions to find a result. So I'm going to start with f of g of 8. So I'm going to work inside out and take g of 8 is equal to 8 plus 2 over 10, substituting in that 8 for my x as my input, and this gives us 10 over 10, or the output of 1. So now if I'm supposed to take f of g of 8, well, g of 8 gave me 1, so now I'm going to take f of 1, and so that becomes 2 times 1 minus 5, which is 2 minus 5, or negative 3, using 1 as my input. So the numerator here becomes negative 3. Now I'm going to evaluate the denominator, I of negative 4. And so it's equal to negative 4 plus 1 squared minus 5. So negative 4 plus 1 is negative 3. Negative 3 squared is positive 9. Minus 5 gives me 4. So when I input negative 4 into my I function, I get out an output of positive 4. And then I go back and I use the output of I of negative 4 and put it into the h function, which is h of 4 is equal to absolute value of 4 minus 7 equals the absolute value of negative 3, which is equal to positive 3. So when I input 4 into my h function, I get an output of 3. So my first part of this is negative 3 over 3. Now I'm going to subtract j of 3. I just need to put in 3 to my j function. So that's equal to 3 to the third power minus 15. 3 to the third power is 27 minus 15, gives us 12. So when I put in 3 to my j function, I get out 12. So in the numerator, I have 12. In the denominator, I'll work inside out. So I'm going to start with g of 98. G of 98 is equal to 98 plus 2 over 10, which is 100 over 10, or just 10. So when I input 98 into my g function, I get out 10. Now I want to evaluate h of g of 98. So h of 10 is equal to absolute value of, whoops, putting in 10 for x, minus 7 is equal to absolute value of 3, which is 3. So in this case, oops, when I put an input of 10, I get an output of 3. So now I have negative 3/3 minus 12/3. Since they're all thirds, I might as well just combine them as is. So negative 3 minus 12 gives me negative 15 over 3, which is equal to negative 5. So this whole expression evaluates to negative 5. All right, let's look at our second composition of functions question. So this time we are working with expressions that we are putting in, and we're going to get out an expression in terms of a. So it says find f of a plus 1 divided by I of negative 5. So we're going to start with f of a plus 1. Our f function, oops, tells us to put in a plus 1 for x, multiply by 2, and subtract 5. So this becomes 2a plus 2 minus 5 equals 2a minus 3. So when I put in a plus 1 to my f function, I get out 2a minus 3. That is my numerator. My denominator is going to be I of negative 5. So I'm going to put negative 5 into my I function. Negative 5 plus 1 squared minus 5. Negative 5 plus 1 is 4. 4 squared, or sorry, negative 5 plus 1 is negative 4, but when we square it, it becomes positive 16. Subtract 5 gives us 11. So our denominator here is 11. We're going to subtract g of 10a plus 8, which is going to tell us we put 10a plus 8 into our g function. So I get 10a plus 8 plus 2 all over 10. Highlighting the inputs. So this is what's input into my function. Well, in the numerator, 8 plus 2 is just 10, so I get 10a plus 10 over 10. And now every term in my numerator and denominator has a common factor of 10, so I can cancel out the 10s, and I'm left with a plus 1 over 1, or just a plus 1. So on my numerator, I get a plus 1 when evaluating g of 10a plus 8. And then finally, I need a denominator, which comes from evaluating j of 2. J of 2 is 3 to the power of 2 minus 15. Putting in 2 to our function. 3 to the power of 2 is 9 minus 15 gives us negative 6. All right. So we get 2a minus 3 minus a plus 1 minus 6. I want to try to combine this into a single fraction. So I'm going to multiply this by negative 6 over negative 6, and this by 11 over 11. And so on my numerator, I end up with negative 12a plus 18 over negative 66 minus 11a plus 11, distributing to all parts, over negative 66. Okay, if I do this subtraction and if I combine this all, I get negative 12a plus 18 minus 11a plus 11 all over negative 66. Ensuring that we are subtracting all parts of the equation, we distribute this negative. So we get negative 12a plus 18 minus 11a minus 11 all over negative 66. We combine our like terms in the numerator, so we get negative 23a plus 7 all over negative 66. Moving to our third composition of functions, we want to find j of negative 5 plus f of 4/5. So j of negative 5 tells us to put in negative 5 to our j function. So we get 3 to the negative 5 minus 15. This is equivalent to 1 over 3 to the 5th power minus 15, which is equivalent to 1 over 3 to the 5th power is 243 minus 15, And we should try to get this into a single fraction. So I'm going to multiply 15 by 243 over 243 to get a common denominator. 243 times 15, I'm going to use a calculator, and we get 3,645. So this is equal to 1 over 243 minus 3,645 over 243, which is equal to 1 minus 3,645 over 243, which is equal to negative 3,644 over 243. Now, the only way this is going to be able to cancel is if we have a common factor of 3, because 243 is 3 to the 5th. So if I add the terms in my numerator here, 3 plus 6 plus 4 plus 4, I get 8 and 9, 17, not divisible by 3. So my numerator is not divisible by 3, and I cannot simplify down. So for j of negative 5, I get negative 3,644 over 243. Now I need to compare that and subtract f of 4/5. So f of 4/5 is going to be equal to, our f function has us take 2 times 4/5 and subtract 5. 2 times 4/5 is 8/5 minus 5. Well, I want 5 to be fifths, so minus 25 over 5. So f of 4/5 is negative 17 over 5. Okay. To combine these fractions, I need a common denominator, so I'm going to multiply 17/5 by 243 over 243. I am going to multiply the purple fraction by 5 over 5. And so I'm going to put this into my calculator. If I do 3,644 times 5, I get 18,220. 5 times 243 is 1,215. And I'm subtracting. My denominator will be, again, 1,215. And 17 times 243 gives me 4,131. So if I take 18,220, which I need to make sure is negative, so negative 18,220, subtract 4,131, I get negative 22,351, all over 1,215. And so I want to know if these can reduce. I know my denominator, 1215, prime factored is 3 to the 5th times 5, because it came from having a 5 in 243, which came from 3 to the 5th. And so I just need to test if my numerator is divisible by 3, because it's clearly not divisible by 5. So let me check. 2 plus 2 plus 3 plus 5 plus 1. So that's 4, 7, and 5 is 12, is 13. It is not divisible by 3, so this is fully simplified. Okay, and for the last section of the review packet, we're going to look at reasoning with some features of symmetric functions. So if we get the vertex of a quadratic function is at -3, -4, and one of the x-intercepts is 0, 0, how can we find the coordinates of the other x-intercept? So let's draw a little picture, help us visualize this situation. So we are given that one of the x-intercepts is 0, 0, and at -3, -4, somewhere down here, is our vertex. So that tells me that we must be opening up. This is half of our parabola, and the other half of our parabola must look something like this. And here would be our other x-intercept. Well, if we know this is 0, 0, and we know this is -3, -4, and we know one more thing. We know that our parabolas are symmetric. So the distance here from 0 to -3 is got to be the same as the distance from -3 to the x-coordinate of our other x-intercept. And that distance is 3, so I have to go from -3, go 3 more, and that gives me -6, 0 as the coordinates of my x-intercept that I'm looking for. So because the function is symmetric, whatever distance I have to go to the center of the function, this line through the vertex, is how far I would go on the other side. Second example, if the vertex of the quadratic function h of x is 2, 5 and f of 1 is 7, what is f of 3? Same idea, let's draw this to help visualize. Vertex is at 2, 5, so let's call that summum up here. Okay, f of 1 is equal to 7. Okay, so that's actually going to be above this, so let me modify my drawing to give a little more space. So I'm going to put the x-axis a little bit lower. If we call 2, 5 this point, our vertex, and then we have another f of 1 equals 7. So this means I have the point 1, 7 must exist on my parabola. We'll put 1, 7, we'll say it's right here. That means that my parabola is going up through this point from the vertex, and since the parabola is U-shaped, it is symmetric, we must be going symmetrically in the other direction. So if I draw my axis of symmetry to go from 1 to the axis of symmetry, I have to go from 1 as my x to 2 as my x. So I would have to go a distance of 1, and that means on the other side I would also have to go a distance of 1. So my other corresponding coordinate here is 3, 7. So if f of 3 corresponds to f of 1, that is the symmetry across our vertex or our line of symmetry, we would say that f of 3 has to equal 7. Okay. Question 3, given the vertex of an absolute value function is 10, 10, f of negative 20 is 5, so that tells me that this point negative 25 is going to be on the graph. F of a equals 5, so some point a, 5 is on the graph, and a does not equal negative 20, so a is not negative 20. What is the value of a? Well, let's visualize this. So I want to draw my graph. My vertex is at this point 10, 10. Then there's another coordinate negative 20, 5, which I'll put out here. That means that this V is open downwards. So maybe it looks something like this. Our axis of symmetry runs through this line x equal 10. And so this coordinate, negative 25, has a distance of 30 to our axis of symmetry. And so on the other side, if we go a distance of 30, we should get some other output of 5 because our graph is symmetric. And so if I go 30 in the opposite direction, that means I should have this coordinate 40, 5. And so A must be 40, 5, or A must be 40 for this to be the coordinate of A, 5. Because the only two coordinates on my graph that are going to have an output of 5 are negative 20, 5 and 40, 5, based on this property of symmetry. So A must be equal to 40. The x-intercepts of an absolute value function g of x are 4, 0 and negative 10, 0. So let's draw this. So I have 4, 0, let's put it here. I also have negative 10, 0. And I know that the range of g of x is negative infinity to 12. So this is a v-shaped function. I know that there's a symmetry, and I know that we go down towards negative infinity, and our maximum value is 12. So if our max is 12, well, that's where our vertex is. We just need to know the x-coordinate of the vertex. And so we get this by using the fact that the symmetry, the line of symmetry goes through the vertex. These two coordinates are equidistant from the line of symmetry. So if I want to know negative 10 to 4, well, the distance between negative 10 and 4 is 14. Half of that distance is equal to 7. So from each of those coordinates, I would need to go to a distance of 7 to get to the axis of symmetry, meaning that the axis of symmetry must be at x is equal to negative 3. Using that fact, I can say the coordinates of the vertex are -3, 12, because 12 is our maximum based on the range. -3 is halfway between -10 and 4, and this has to be a symmetrical graph because it's an absolute value function graph. Okay, with asymptotes, why does the exponential function to the x have an asymptote at y equals 0? So to answer this, if we put in positive inputs to our function to the x, we are going to tend towards infinity. So the more positive that we put in, the closer and closer to infinity that we will get. However, if we put in negative inputs, 2 to the -1, this is equivalent to 1 over 2. 2 to the -2 is 1 over 4. 2 to the -3 is 1 over 8, and so on and so forth. So in this direction, we are getting infinitely large. In this direction, if we get more and more negative with our inputs, we are getting infinitely close to 0, because 1 divided by some really big number gives us a really small number. So as we input negative values to this function, and as we put in really big negative values, we get closer and closer and closer and closer to 0, but we never actually get there. Like if we put in 1, or say, if we took 2 to the -10th power, this is the same as 1 over 2 to the power of 10, which is 1 over, let's check in a calculator, 2 to the 10th is 10 or 1024. As a decimal, 1 over 1024 is equal to 0.0009765,625. And so we can see that this is pretty small, but we can plug in anything we want. We can plug in -1,000,000, -1 billion, -1 trillion, and get smaller and smaller and smaller decimals that get closer and closer and closer to 0. And so that's why our exponential functions have these asymptotes, because they approach 0, but they will never get there, and they will certainly never cross 0. Okay. And then this second question is the same idea. From this 5 to the x, this also approaches 0 for negative inputs. Just like 2 to the x creates an asymptote at 0, 5 to the x approaches 0 the more and more negative of an input we put. So say we put 5 to the -3, that's equal to 1 over 125. So that's already pretty small. If we put in 5 to the -4, it's 1 over 625. So as we put in more and more negative values, we're getting closer and closer and closer to 0. However, what we do after we get closer and closer to 0 is we always just add 12. So plus 12, plus 12. So we're essentially taking 12 and adding on some tiny, tiny decimal and saying we're getting closer and closer and closer to 12 because it's basically 0 plus 12. So our graph would look something like this with an asymptote at 12.